Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to think all things maps. A little overview for beginning with, we're going to focus on the map scale or map scales. We'll then compare some different types of maps, some isoline maps, and think about what those are. And finally, we'll end with a focus on digital geography. All right, so what is a map scale? Scale is essentially a fraction, so a big fraction or a small fraction. And so a small scale would be a small fraction. So think 1 divided by a really big number. So lots of zeros and decimals. So a small scale then represents a large geographic area with a limited level of detail. So think like state borders and boundaries. So again, a small scale is like a very tiny number, 1 over 31 million here. Whereas a large scale or larger scale would be a larger number, 1 divided by a smaller number, or in this case, so 1 over 500,000, or as we'll see later, many of our topographic maps are 1 to 24,000. And so that's a large scale, which represents a small geographic area with much more greater detail. So in this case, you could potentially even see buildings or rivers, bridges, etc. And so small scale versus big scale. So small scale, large area, large scale, small area. So the map scale is a distance ratio that exists between features on a map and the real world. And so in this case, we could write it something like if you measure 1 centimeter on the map, that could represent 24 kilometers in real life. Often in many of our published maps, it's the map scale, this distance ratio is published as a representative fraction. So 1 centimeter equals 24,000 centimeters, or 1 to 24, or in that case, whatever unit of measurement that you are using. So 1 inch equals 24,000 inches, or 1 centimeter equals 24,000 centimeters. It's a representative fraction. And finally, here on the bottom, many and most published maps have some form of a graphic scale that then matches this representative fraction. So as described, 1 to 24,000, and it would show you that exactly this distance from 0 to 1 is representing that distance in kilometers or meters. Okay, so let's kind of go through a couple scale applications, or at least one application of how to do this. And so, for example, here is what's called the Marquette Quadrangle. It's a topographic map published by the U.S. Geological Survey, and it depicts the 7.5 by 7.5 minute degree minute second latitude and longitude space. And so it is a large scale map that represents a small geographic area with quite a bit of detail. And so in this case, this published map is 1 to 24,000. And so you would measure a distance between point A and point B on a map, and then you use that representative fraction to determine if you measured this, how many centimeters or inches that is in real life. And so it does involve a little bit of math. Finally, you may need to convert that. And so if you converted 1 inch to 24,000 inches, many of us don't really think of space. So like, I'm going to walk downtown, it's going to be 1 trillion inches or something like that. And so you might need to kind of further convert it into a meaningful distance from like inches into miles, for example. And so let's go and kind of provide one example. So if you were to walk from here at NMU on campus and you wanted to go jump off of Black Rocks, you measure that distance on the actual map and you find that it is exactly 18 centimeters. You then determine that the scale, the representative fraction of this map is 1 to 24,000. You could then, multiply 18 by 24,000. And so then you understand, or then we can show that there's 432,000 centimeters between NMU's campus and Black Rocks. But many of us don't really think in centimeters. However, kilometers is more representative. You could then even further convert kilometers into miles if you would like, but here 432,000 miles is 4.32 kilometers, almost a 5K race, if you will. All right, so that's a little bit about scale. So now we're going to move into describing different types of isoline maps, and we're going to pay particular attention to topographic maps. So maybe as a hint, as I just kind of gave it away, can you name one type of isoline map? In fact, it is a topographic map. Many of us have likely seen a map, something like this, on a computer or printed. And so these represent elevation. Each of these brown lines is a contour representing equal points of elevation. If you've ever watched the evening news, you probably have seen a map, something like this, showing equal temperature. So these lines representing equal points of temperature. And so this isoline map, as we'll later define, is called an isotherm. And so there's many different forms of weather isoline maps. It could be precipitation or pressure, or in this case, temperature. So many of these maps we're familiar with, although maybe we haven't investigated into a little greater detail. So here, let's begin our journey into isoline maps, thinking about topographic maps. And so topographic maps contain contours that connect points of equal elevation. So if you follow one of these brown lines, you are following exactly that same elevation. And so just to kind of like re-project this 2D into kind of a 3D image, you can kind of see how these topographic lines work, where this 2D plat image could be like re-represented into a three-dimensional landscape. So some kind of take-homes to practice with these type of maps. Anytime you have lots of lines really close together, that represents a steep area, so a steep incline. And then anytime you have lines that are further apart comparatively, that area is relatively flatter. In this case, as there are many instances on this map, anytime you have a closed circle, so a line going perfectly around, that represents a hill or a mountain. Locations where there's V shapes, so the line itself comes and then it stops and then it goes back the other way, so it's a V shape, that represents a valley. And so you're kind of going through thinking like you're hiking up a creek wall, and then you kind of stay at the same elevation, you get to the creek and you come back on the other side of the creek. And so that represents a valley. And then in some cases, it's not as common, but in some places there are essentially, instead of a hill, you have a depression. And so then you still have concentric circles, but in that case, and on a topographic map, it would be marked with little hatches. So there'd be little dashes on the inside of those lines to represent the fact that it's a depression and not a hill. So let's look at those examples kind of applied here, or revealed, if you will. And so here is an area with lots of lines close together, meaning it's a steep slope. At the top of this mountain, as it is, the lines are quite a bit further apart. So it's probably kind of a broadly topped mountain, and then all of a sudden especially here to the east, it's falling off and becoming much steep. So steep slope versus a flatter area. Here you have many concentric rings going around and around and around. And so that's representing a top of a mountain or a hill going down in each direction. Here's a classic example of, here's the stream. The stream's actually flowing down this way. And then here's your equal contour line and then coming back on the other side. And so you could kind of think about it like walking at the equal elevation, the stream's below you, and you can stay at that elevation until you get to the creek and then come back on the other side of the river. So these maps will have published graphic and other representative scales. They'll also indicate, or you can look at the lines to determine what the elevation difference between each singular line is. Often in many of these maps, at least USGS quadrangle maps, it is 20 feet, and then it's 100 feet between bolded lines. You can kind of see some of these lines are bolded, for example. So a little bit more topographic interpretation for your reference. Here's kind of a zoomed in section. So similarly, we're looking at a 1 to 24,000 map. There's a creek down here called the West Branch of the Neversink River. There's a couple mountains named here, Hemlock Mountain and Spruce Mountain. Let's say you woke up and you're down here on the creek. You're like, I'd like to walk up to Spruce Mountain. I wonder how far that is. So let's think about how you'd figure that out. So first, you also maybe are thinking, how high is that mountain? So you can use these contours. Here's 3,000, and going up, here's a bolded line marked at 3,300. So 20, 40, 60, 80. There's 4 more contour lines above that. So remember, concentric rings represent a mountain. So you're going up to 3,300. You keep going up. There's not another boulder line, so we haven't reached quite to 3,400. And so here we're at 3,000, or sorry, 3,000 to 3,400. Yeah, so 3,382 was my estimated top, where this line itself, this top ring, represents 3,380. And then looking close, if you followed all the lines and came all the way down, my interpretation of the elevation of the river was right at 2,218 feet. And so you can figure out the difference of 1,164 feet. So you would climb 1,164 feet from the river to reach the top of Spruce Mountain. You could then determine the distance on the real map using a ruler. So if you measured the distance between here and here physically on the map with a ruler, that distance was measured as 13 centimeters. And so if that distance was 13 centimeters, you then would say 13 multiplied by the representative fraction of 24,000. And then we could further convert that from centimeters into inches, and then finally into feet by dividing by 12. And so 13 centimeters here representing 10,236 feet. We could then divide the height over the distance to get the slope. And so for every foot you walk, you'd be going up 1/10 of a foot on average on that slope. All right, so some added interpretation of quadrangle maps, and here actually the corner of the Marquette quadrangle, the USGS published map. And so there's a lot of information on the border of these maps. And so what does it all mean? So every map, every USGS quadrangle map depicts latitude and longitude, so degrees north of the equator and degrees east or west of the prime meridian, going back to the previous lecture topic. And so they're marking it as degrees, minutes, and then potentially seconds. And so there's 60 minutes for every 1 degree, and there's 60 seconds within every minute. And so here we're marking degrees and minutes in the corner. And so again, 46 degrees in 30 minutes. So 30 divided by 60, 46.5 degrees. In fact, north of the equator, and then here 87.5 degrees to the west of the prime meridian. Other markings, so then here's the corner marking, and then so you would go from 87 degrees in 30 minutes, and so we're going closer to the prime meridian, and so we actually have decreased from 30 minutes to 27 minutes and 30 seconds. Not a major take-home of the course, but if you were to take a class like maps, for example, you would explore this in much greater detail, again, thinking the fact that there's 30 seconds within every 1 minute, and there's 30 minutes within every 1 degree. Okay, so moving on, there's additional or different grid systems. There's actually 3 distinct grid systems indicated on the edge of these USGS published quadrangles. The other one, the US Public Land Survey System. And so all of these horizontal red gridded lines representing that US Public Land Survey System. So again, townships north and south of the baseline and ranges east and west of that principal meridian line. So here indicating we're 48 townships north of that baseline, and this actually is the marking of Township 47 North. So everything below my cursor, Township 47 North. And similarly, while this is zoomed in, there's the section numbers. So remember, there's 36 sections within each singular township and range. So here's section 31, for example. Last but not least, another very common use of grid system is using the Mercator projection. And so this is universal transmercator, which is in meters. And actually, this is in millions of meters north of the equator, and then meters actually here to the actually that way to the east of. And so for the UTM system, kind of like USPLS, there's a principal meridian and baseline, but in this case, there's a zone. And so we're in a specific zone within UTM. And so this is meters east of the zone line, kind of like based upon meridians. Okay, so I think that's enough focus on topographic maps. So moving on. So now we're just going to think a little more broadly about some other common types of isoline maps. So one of them is an isotherm. And so as we already kind of thought about, so these lines, and then in this case, it's shaded or colored, the lines are connecting points of equal atmospheric temperature. And so in this blue shaded area, it's about 15 degrees. And so here an isotherm representing equal points of temperature. In isobar, here it's a little fainter, but these white lines representing equal points of atmospheric pressure. We'll come back to this later in the semester when we think about weather and climate, but ultimately here weather and weather systems, as this is the most influential set of data that influences weather and our ability to predict weather. So here again, these faint white lines connecting points of equal atmospheric pressure, known as isobar. An iso-Hyatt map here connecting points of equal atmospheric precipitation. And so here is a 10-day, a previous 10-day snowfall forecast by John D., a local weatherman. And then just you could present these maps all over the world. So think about Australia. Here's mean rainfall in kind of the winter, spring, or in their case, the summer down in the southern hemisphere. For Australia, I would say this is probably one of my favorite maps. Oops, sorry for that click. Here's a picture, an old picture of me in the middle of a wilderness area with my dog Gabbro. But often I'm always, especially in the winter, looking ahead to the forecast to think when the best day for untracked powder skiing is. All right, so moving on, also thinking about isopac maps. And so here an isopac is connecting points of equal sedimentary thickness. This is a type of a geological map. Here's a map of the Michigan Basin, also something we'll return to later this semester to think more critically about. But here, connecting points of essentially like equal depth of bedrock in these areas. And so here, the Michigan Basin. Here's kind of a work through digital example of how you would interpolate these data. Here's like an actual map of temperature in February in the US. And so 20 degrees, 35, 40, 51. And so when we draw these ISO lines, in this case for temperature, a 10-degree ISO line would connect to any station, so any weather observation that's exactly 10, and then it would be anything outside of it is larger or warmer, and anything inside is cooler or smaller. And so here we see our lower temperatures. So I have this kind of, you could go ahead and you could try to do the 20. So you would go through 20, you would go between 22 and 16. Here's another 20. It's going to be on this side of 23, for example. And so here is a digital version of some of these ISO lines worked out and how you would interpolate them. So there's a 20-degree line, a 30-degree line, a 40-degree line, and last but not least here, a 50-degree line. And so then kind of going back to some of these other isotherm maps, you could then kind of shade them in if you want to make them look very pretty. Going all the way through. Okay, so that's enough about isoline maps. And so now let's turn our attention to digital geography. So there's many ways to remotely sense Earth's surface and many different observations and properties we can do so. But here we're going to like capture the basic major differences. How do we collect these data? It could be from a plane, and so aerial photographs. In that case, a plane is flying over and it's literally taking pictures at exact known time intervals in succession, knowing exactly where the plane is, and then you can view this landscape in a systematic way. You're literally putting pictures next to each other, and then in rows as the plane would fly, and then it would kind of turn and come back and do another transect and another one, kind of going in like a grid pattern like this. And so you could literally take all these pictures like this person is doing and put them all together to make one very large map. And then if you were to fly that and then fly that same grid system a year later or months later or years later, you could look at change over time. So still, there's a lot of observation collected both from planes as well as now more and more via drones. But most of the digital geography, most of our digital mapping largely is coming from satellites. And so there's really two major types of satellites that we're going to focus on. One is called sun synchronous. And so these satellites literally have a nearly polar orbit. And so they orbit around the Earth and they will return to the same exact latitude approximately 99 minutes later, which if you think about it, that's pretty darn fast. I mean, we'll fly from one continent to another. If you fly from New York to London, for example, that's a many hour flight, like a several hour flight. This satellite is going all the way around Earth, meanwhile taking tons of pictures and collecting lots of data, and it's coming all the way back to the equator in 99 minutes. That's incredibly fast. And then the Earth is revolving or rotating rather underneath that space. So as it's revolving, or so as it's orbiting this north-south orbit, the Earth is rotating, and then it will actually come back and it will repeat that same path approximately 16 days after it returned. And so it's always going to be recording data at any place on Earth. When it comes back 16 days or 17 days later, it will be literally capturing that same picture from that same point in time at the same point in time. So that can be really useful also for thinking about land use change over time. How is the landscape of Earth changing over time? We have these repeat photos collected about every couple weeks, and then every couple weeks later and later, and then you could stack all those up and look at change over many months and years. These satellites have a very low Earth orbit, so they're actually quite close to Earth's surface. While that doesn't seem close, that's pretty close in the grand scheme of space. And so all of these sun synchronous orbits are very low or low Earth orbits, and they're very fast and they're polar, some key take-homes. So here is kind of an integrated animation to show you how this sun synchronous orbit works. And so the satellites are orbiting approximately polar, so north to south, and then they're passing over the equator. And as it does, 99 minutes later, it returns and the Earth has rotated underneath it, so to speak. So here then a very widely used example of a satellite. Here's the Landsat 8. It is a satellite that is sun synchronous, and it is co-funded by NASA, by NOAA, and by the USGS. They collect data like a picture, and that picture is 185 kilometers wide. So that's a pretty wide picture, and it has 15-meter resolution. We'll come back to resolution in a little bit, but essentially every cell is 15 meters wide, which is pretty coarse when you think about it. It has two major sensors on board, and then kind of going back to this, so the Landsat 8 is a sun synchronous orbit, just like this. Oops. And then it's coming back in approximately 16 or 17 days later, 2 weeks later, it's coming back, and it will come all the way back to where it started about 2 weeks later. So I'm going to highly encourage you to click and watch this really useful kind of video. It's very short, and it depicts the Landsat satellite series as an example, and it also kind of like reinforces this sun synchronous example. All right, so as I mentioned, then here, 15-meter resolution. How many people have taken a picture and those pictures are really grainy and pixelated? Well, with our phones and our cameras, you can take pretty darn good pictures these days. Some cameras are better than others, and older cameras are often pretty pixelated. And so from a satellite perspective, again, it's taking this picture that's literally 185 kilometers of Earth's surface wide, and then every single cell, more like this, is 15 meters wide. And so probably more like this, where some low-flying planes and drones and even some satellites have much higher resolution. So now we're going to compare sun-synchronous orbits to what is a geostationary satellite. So these are two very different types of satellites. A geostationary satellite remains in the same place over Earth's equator at all times. It literally rotates above the equator with Earth, and so it's always fixed at that one location. And so here are some links to find weather from NOAA here. That satellite is always fixed right above the same spot, and it's over time then you're going to see weather, in this case clouds and temperature, change over time. So it's a way to kind of observe everything changing underneath you where the satellite itself is not moving. Major differences here: a geostationary satellite is very, very far above Earth's surface. It has a high elevation orbit. So again, it's fixed above the equator, and it is approximately 35,800 kilometers above Earth's surface. So much, much, much higher than those sun-synchronous satellites. These geostationary satellites, while I'm showing a weather satellite here, they're also very commonly used for all of our communication. So if any of you have ever had satellite TV, like a satellite dish for TV, which is becoming less common, but perhaps some of you have, those satellites mounted on your roof or outside literally are always pointed to the south horizon, and they're pointed exactly at this geostationary satellite by Dish TV or whoever owns it. So for weather and communications. Many of these satellites are equipped with many different sensors, not just visible range, but all across electromagnetic energy. So we'll talk more about electromagnetic energy later this semester, but for now, appreciate that we can observe energy in many wavelengths that aren't just in the visible spectrum. In that case, it's essentially data, how much energy is taking place or occurring at different places on our surface, and then we can add color to it. So you can assign a large value, a red color, and you can assign a smaller value, like a colder temperature, a blue color, and then you can have a shade or a ramp in between to represent that passively collected. So that in that case, the satellite is simply receiving that data. It is not sending any information out. It's just receiving what's there underneath it. And so again, we have these kind of false colors. We're going to add color to enable or aid our interpretation. There's other types of satellite measurements, and these are synthetic aperture radar. And any type of radar is what's called an active method. And so in this case, if a SAR or synthetic aperture radar is mounted to a satellite, literally that satellite is sending out radar waves. Those waves bounce to the ground and then return to the satellite, at which point the satellite or the sensor is interpreting that return velocity, the time, the angles, and it's using that to collect data. So radar is this active form of remote sensing. All right, so here, kind of wrapping up, many of us have likely used GPS. Well, maybe we really realize it or not. Now it's integrated into all of our smart devices. But a GPS is a global positioning system. And so how that works is within your phone or a handheld GPS unit here, your phone or the unit is literally receiving signals. So this is very much active from a network of satellites that are orbiting above Earth's surface, and those orbits then they're not necessarily sun synchronous. They're all orbiting, and the goal actually of this network is that there's several, at least three, as we'll learn, satellites above you in your horizon view, if you will, at any given time. And so that this device then is literally receiving signals from any and all satellites that it can communicate with, and it then is using that to determine your location in latitude or longitude or any of the other projections at any given time. And so we're using it to determine our location on Earth. And so these satellites, one network, for example, has 24 satellites that orbit Earth every 12 hours. And so they're all moving and orbiting, and the goal again is to have kind of full coverage of the Earth at all time. Now there are many networks, and so there's a network that was primarily funded by the US, and then other networks funded by other countries and regions, and there's many joint ventures. So there's many GPS satellites. There's really two major networks that many of our devices interact with. And so this is kind of interesting, like data science. It's actually transmitting what's called pseudo-random code, and it sends it in pulses. And so there's actually like numbers being sent in little pulses, and those pseudo-random code transmissions are what your receiver, literally your phone, is receiving and enabling it to determine its relative position on Earth's grid in latitude and longitude. So a little bit more about how this works. We need, or like your phone or GPS unit needs to connect to at least 3 different satellites called triangulation to allow you to determine your location in X and Y and Z for elevation. So latitude, north and south, longitude, east and west, and then elevation. Many of these units, or if you have a handheld GPS unit, it'll actually tell you how many satellites it's connected to. So often you're able to connect to more than 3, even 4, 5, 6, or 7. And the more that you're connected to, the better accuracy you have. And so meaning that you are here plus or minus 5 feet around you, or if you are only connected to 3 satellites, it might say you're right here, but we're only sure you're right here plus or minus 100-foot radius. So we think you're somewhere around there. Something that commonly happens with GPS, and this can happen naturally with cliffs and trees, and then often in cities, and it's very common in cities, as those pseudo-random codes are actually coming down and they're bouncing off of physical objects. And then your phone is receiving that pseudo-random code, but your phone or GPS unit does not know that that signal had bounced or had been deflected. And so that is going to cause error. And this is called multi-path error. And it's deflection of these incoming signals from the satellites where your phone still receives them again, but it doesn't know literally that that signal had been deflected. This is actually pretty common, especially if you're in a big city and you're trying to use a GPS. Often you can, like, I don't know, maybe some of you have actually seen this. If you like get out your Google Maps or whatever map program you use and you're like looking and it says you're here, and then sometimes it literally just starts kind of drifting and it's like, wait a second, it says that I'm on the other side of the street, and then it kind of comes back and it kind of keeps moving. And that's exactly what's happening, is this multi-path error. Ultimately, we can use all of this data collected by satellites in all forms, and we can store that data and then project it into a space and then store it in a file. But we can kind of overlay that. It could be temperature data or precipitation data. It could be physical elevation. It could be city and infrastructure imagery, et cetera, et cetera. And we can actually then take all of those different layers of data that have been collected by these different satellites and different sensors and stack them on top of one another and think about relationships and comparisons. And this is what's called a geographic information system. And so this is a very common and continuously emerging field, allowing us as humans to better understand, better plan, better predict activities and relationships. So that concludes this lecture topic. Later this semester, we'll likely come back to this National Geographic Map Maker, as it's called, which is a really kind of handy way to better familiarize ourselves with GIS and layers to kind of think about Earth's surface and these different properties. So with that, Dr. VG is signing off.